Hello, my name is Wade Adams, and for my GIT 335 project, I want to take a look at quantum computing. We're going to look at the science behind quantum computers, we're going to compare them to our standard daily use computers, and then we're going to take a look at the applications, both what they're doing now and what they're going to be doing in the future. The term quantum gets thrown around a lot these days. You hear quantum mechanics, quantum physics, quantum dots. What quantum really is a look at subatomic particles. So when we talk about quantum mechanics, we're actually talking about the study of the motion and interactions of particles on a subatomic level. That is, the electrons, the protons, the neutrons, and any other subatomic particles that we may not have discovered yet. All of the science behind quantum computing is extremely advanced, and it takes a long time and a lot of research in order to even comprehend the most basic principles of quantum mechanics. For the purposes of this video and this project, I want to take a look at some of the most basic concepts. One being electron superposition.
For the purposes of this video, I'm choosing to examine electron superposition. But what's important to consider is that any particle can also have a superposition. The green ball in the center of this graphic represents a particle. The 1 and the 0 represent the two different states that a particle is thought to have been able to be in, either the 1 state or the 0 state. In classical computing, the 1 state and the 0 state represent the on state and the off state of all the different transistors in the CPU. Breaking the software code down to its most basic level, switching that transistor on or off, this allows us to have a hardware change from a software change. Now, superposition defines a reality in which the particle can be in either state. So instead of being in a 1 or a 0, it can be in a 1 and a 0. The trick is that once the position or the amplitude of the particle's wave has been measured, it no longer has this superposition. Instead, it has a defined state. The only way that we are able to use superposition is by calculating the probability that the particle will be in either the on or off state. A series of highly complex mathematical equations and algorithms are able to utilize the particle superposition in order to take an input and generate the output. In the case of quantum computing, this input could be a highly complex modeling problem, and the output would be the answer or the simulation to that problem.
Now, we haven't even begun to scratch the surface of quantum mechanics or quantum physics, but electron superposition is extremely important to understand in order to consider how quantum computers work. So now I'd like to take a look at exactly what it is that makes a computer quantum by comparing it to a traditional computer. When we start to compare quantum computers to traditional computers, there's a couple of key pieces of information that we have to think about. A traditional computer relies on bits. A bit is essentially the smallest form of software programming or data that a computer can utilize. And essentially a bit, it can either be a 1 or a 0. And what that means is that the tiny transistor or the tiny switch is in the on state or the off state. Now, qubits are the quantum cousin of regular computer bits. And they're the quantum cousins because they are the base amount or the base unit for software programming when it comes to quantum computers. But they're different from bits because they utilize the electron superposition. So when programming with qubits, you're not restricted to the either on or off state. You can actually utilize the probability that the switch will be in either state in order to solve more complex algorithms. The best way to describe how a quantum computer works in terms of handling the information is best done with an analogy to a maze.
Now in this graphic, we have the same maze being done by a classic computer and a quantum computer. In the classic computer, the processor is going to try each solution one at a time. So you can see this in the red line that goes to the first option, finds a dead end. Then it goes to the blue line, looks for another option, and then gives us a dead end. The classic computer's processor is going to keep making attempts one at a time until it finds the correct solution. With the quantum computer, assuming it has the correct number of qubits in order to handle the possible number of solutions in this maze, will attempt all of the different routes and options at one time and output the correct option or series of options. The reason that quantum computers are exponentially faster than classical computers based on the number of qubits is because rather than trying to brute force attempt to solve a problem, it completes all of the possible solutions of that problem at one time and outputs the correct solution.
Quantum computers become exponentially more capable of handling more amounts of data the more qubits that they have.
If we take a look at a 2-bit system, there are 4 possible transistor state combinations in a classical computer. You can have 00, 01, 10, and 11. The interpretation here is that you can get 1 bit per transistor at a given moment of time. With a quantum computer, rather than having to go through each step individually, the possible outcomes are compressed into a singular step. So there can be 4 different solutions, but they're all calculated at the same time. Based on the number of qubits, you can have exponentially more information being handled at any given moment of time. And that interpretation is 2 to the nth power, where n is equal to the number of qubits. It has been proven that if you have a quantum computer with 300 qubits and you consider the interpretation laid out in this graphic, that you will have 2 to the 300th power, which is more possible outcomes than there are known particles in this universe.
Quantum computers are best utilized when dealing with complex algorithms and lots of numbers. Now, one process that I don't want to get too much into is the generation of bitcoins or cryptocurrency. Essentially, cryptocurrency is created by completing these highly complicated processes that take standard desktop computers tons of time to produce any amount of information. A quantum computer would be extremely beneficial in this scenario and generate cryptocurrency at an extremely quick rate. Another excellent use for a quantum computer would be the rendering of highly complicated and high definition models. For instance, the generation and simulation of atoms or space systems. A quantum computer would excel in these areas because there are highly complicated algorithms that run the operations of a simulated universe. Quantum computers will be extremely necessary when we start to look at more advanced artificial intelligence and neural networks. Artificial intelligence is extremely computationally heavy at the moment, and our standard computers take a long time in order to process the kinds of mathematics and computations that are necessary in order to get an artificially intelligent device. So, when quantum computers become more accessible to developers and more easy to operate, you will see a huge movement in order to get these quantum chips onto smaller form factor devices that might allow us to have artificially intelligent robots or neural networks on a smartphone. By increasing the efficiency and decreasing the size of the devices, we will be much more capable of completing these extremely intensive tasks such as artificial intelligence and neural networks on smaller form factor devices.